All right, now we will start the examples. Going back to example 1, graphing the step functions. We'll start with f of x equals the greatest integer of x plus 1. And once again, these will be double brackets. Sometimes we use single, but we'll use double there. So what we're going to do is kind of get this idea of a t-chart. And there's a couple ways you can do this, but kind of the way that I think about it is if I plug in 0, I get the greatest integer less than or equal to 1, which is 1. But what happens when I plug in 0 all the way up to 0.99999? Well, I still get 1.999, which is still 1. So no matter what value from 0 to 0.99, I always get an output of 1. Once I get to 1, it steps up to 2. So anything from 1 to 1.99999 will give you an output of 2. And you can kind of keep the same idea going. If you go to 2, it jumps to 3, but that's anything from 2 to 2.99999. And once you get a couple in there, you can go ahead and graph. So when x is 0, your output is 1. And everything from 0 to 0.999 is going to be 1. And then it's going to step up. At x equals 1, it steps up to 2. And everything's 2 until it gets to x equals 2. And then at 2, it steps up to 3. And so you can just kind of keep that same process going. Once again, make sure you get that open circle at the end of that value there, because there's not a point there. There's not a point at 1, 1. There's a point at 1, 2. And there's your step function. And there you go. On the second one, you can try it on your own, or you can watch to see how this works again. I'll do the same thing. So I'm going to do x and g of x. And I'll kind of start the same way. If I plug in 0, 0 times 2 is 0. 0 minus 1 is negative 1. But it's not just 0. It's everything from 0 to 0.99999, because the greatest integer less than or equal to 0 or 0.999 is always going to be 0. 0 times 2 is 0. 0 minus 1 is negative 1. But once I get to 1, the greatest integer less than or equal to 1 is 1. 1 times 2 is 2. 2 minus 1 is 1. But that's everything from 1 to 1.99. 99 keeps going. And that will be 1. And then from 2, it steps up. So that will be 4 minus 1 is 3. But that's everything from 2 to 2.99999. And you can see the y value is going up by 2, and that has to do with this. And we'll talk more about transformations, but it's stretching it out. So we can go ahead and graph this. From 0 to 0.999 is going to be negative 1. So from here. And then at 1, it's going to jump up to 1. And at 2, it's going to jump up to 3. And then at 3, it's going to jump up to 5. And so on. And that's your greatest integer functions. And the last set of examples that we're going to do are these functions even, odd, or neither? So to go through and prove this, you want to identify even. Remember, when you plug in the opposite of x, you should get just the y value, which is f of x. If it's odd, when you plug in the opposite of x, you should get the opposite of y. So that's how you're going to prove whether these functions are even or odd or neither. Now, if you think about an even function, it's symmetric to the y-axis. This is a quadratic. All right, think of the shape of a quadratic. Is that going to be symmetric to the y-axis or symmetric to the origin? It's going to be symmetric to the y-axis if it is symmetric. So really, you can pick and choose which one you want to check first. On this one, I'd say let's check even. So we're going to plug in negative x wherever there's an x and see if that equals the original function of x squared plus 1. Well, when you square negative x, you still get x squared. So on this one, you have proven that f of x equals x squared plus 1 is an even function. So we know it's even, and the reason we know it's even is because f of negative x is equal to f of x. Alright, so for part B, we got g of x equals x cubed minus 1. Once again, if you picture what the graph looks like, is that going to be symmetric to the y-axis or the origin? Well, more to the origin, not the y-axis. So if I was, going to guess which one it might be, I would do odd first. So I'd say f of negative x has to equal the opposite of f of x. So the opposite of x has to equal the opposite of y. Plug in a negative x wherever there's an x. And then on this one, you do the opposite of the function. So it's negative the quantity x cubed minus 1. So on the left side, if you take negative x and cube it, you still get negative x cubed. So that's negative x cubed minus 1. On the right side, when you distribute the negative, you get negative x cubed, but you get a plus 1 instead of a minus 1. So these are not equal. So it is not an odd function. So if it's not odd, do I have to check even if I know that the graph looks the way it does? The answer is yes. You still need to check and prove that it's not even. So we would say f of negative x, is it equal to f of x? Well, we already did f of negative x, which was down here. That was that one. So we already know that that's negative x cubed minus 1, and the original function was x cubed minus 1. So you can see that those are not equivalent as well. So this is neither, because neither one shows that they are equal. And now the last example is another cubic. So once again, if I was picking, I would pick odd first, just based on knowing what the graph is going to look like. So I'll do once again f of negative x, if it's odd, should equal the opposite of f of x. So we'll plug in a negative x wherever there's an x, and then we'll do the opposite of the original. And so negative x cubed is still negative x cubed, and then you have the opposite of negative x, which is plus x, and then you distribute on the right hand side to get negative x cubed plus x, and there you go. You see that they are equal, so we know this is an odd function because f of negative x is equal to the opposite of f of x. So once you prove it's odd, you don't have to check for the even. Okay. Once you figure out one of them, you don't have to do the other. So that is it for this section of graphs of functions part 2. So be prepared in class to have some of these discussions about what is the rule for symmetry to the x-axis, and then also what is the only function that is symmetric to the x-axis.